Okay, so what we're going to start looking at today, if you're going to sit back there, you got to focus and be quiet, not distract other people, okay, and not be distracted by other people. All right? All right, so we're going to look at polarity in larger molecules. So this is going to require that you think a little bit differently than we did in Unit 4. Okay, we got to progress beyond Unit 4. So the first thing I'm going to look at is a molecule like this. This is our example molecule here. Okay. Now in Unit 4 we looked at molecules. Let's see. What am I trying to think of here? Organic molecules that only had hydrocarbons. That were only hydrocarbon groupings. What I'm going to do here is add a different kind of grouping to that hydrocarbon. Okay. I'm going to add a different kind of grouping to that hydrocarbon. Now, if you remember from Unit 4, when we have a grouping like this, CH3, what it means in terms of a Lewis structure is that I have 3 hydrogens single bonded to that carbon. And if I have a grouping like this, that means I have 2 hydrogens single bonded to it. And if I have a grouping like that, they're the same thing, 2 hydrogens single bonded to that carbon. But over here on the end, I've got an oxygen and a hydrogen. Okay, what I want to know is what polarity does there exist in a structure like this. All right? Like Ryan, you're supposed to be taking notes, buddy. Okay. So what I want to look at right now is just this part of the molecule. Just that part right there. Yes.
So what if that was CH3OH?
Well, it would be the same basic idea. We'd only be looking at one part of it.
So you would put an H after the C, last C, and then an OH?
No, because if I put an H here, it stops you can't put an OH after you put an H here. Because H's can only have one bond. That's why they stop with just one bond here on each one of these. Okay? So what I'm going to do is I'm going to look at how I put together these 3 atoms here. And in this case, in Unit 4 and last week when we were looking at polarity, we looked at small, simple molecules. Now I'm going to look at part of a larger molecule. Polarity in larger molecules. Okay? I'm only going to look at this part right here. So what I care about right now is the electron dot formula for oxygen. You should know how to figure out how many electron dots oxygen has. That was part of the quiz on Friday. You should be able to figure out the electron dots for hydrogen and the electron dots we need for carbon. Now, because I'm only looking at this part of the molecule, for this examination, I'm ignoring these 3 bonds here on this carbon. I'm only looking at the bonds that surround the oxygen. I'm only looking at the bonds that surround the oxygen. Okay? So, I can share those 2 electrons there, and these 2 electrons here, and I'm getting a sharing arrangement that only applies to the oxygen. A sharing arrangement that only applies to the oxygen. So I started with with electron dot formulas for hydrogen, oxygen, and carbon. Now that I've circled some and showed the sharing of those electrons, I have a sharing arrangement, but just for the atom of interest in this case. The atom of interest in this case. Okay? From there I'm going to get, I'm going to squeeze the electrons in between the 2 atoms. I'm going to squeeze them together and get a sharing, a Lewis dot formula. So here's oxygen. Got 2 lone pairs here. I've got a shared pair which I squeeze between the oxygen and the hydrogen, and a shared pair which I squeeze between the oxygen and the carbon. All right. Now I don't really care about these other bonds. That's what I said. We don't care about these other bonds at this point. Just for this examination, for this limited purpose, we're only looking at whether this is a polar location on this larger molecule. Okay? All right, now we know that there are other electrons over here, but we're not going to look at them. We're not going to consider them right now. All right, now from this, then we can get a Lewis formula where we replace shared pairs with lines. So between this oxygen and hydrogen, I've got a line. Between this oxygen and carbon, I've got a line. And then I've got the lone pairs on the top and the left. And we all know that, just reminding that there are some electrons down here. They are bonded, but we don't care about those right now. We're just looking at what's going on with the oxygen itself. All right. So, how many sets of electrons do I have around this central atom? 4 sets. What geometric shape do you have when you have 4 sets of electrons around a central atom? Tetrahedral. So around, for this oxygen itself, just that oxygen, there's a tetrahedral arrangement of those electrons. And that looks just like the kind of stuff we did last week. Okay, we have a tetrahedral arrangement of the electrons, the sets of electrons around that central atom. So I've got 1, 2, 3, 4 sets of electrons around that central atom. And I've changed that from a 2-dimensional shape to a 3-dimensional shape here to show those 4 sets of electrons. 1, 2, 3, 4 in a tetrahedral arrangement. And I want to do the same sort of thing we did last week. We replace those sets with the atoms if they are shared. And I've got 2 sets that are shared, here and here. Okay, so I'm going to redraw this shape where I have a hydrogen. Say what? Oh, I'm sorry. Yeah, it's supposed to be an oxygen. So I'm going to have a hydrogen up here where I'm going to share this set here. I'm going to have a carbon down here where I'm sharing this set, and then I've got the 2 lone pairs out here. Doesn't matter whether you put them on a tetrahedral. Does not matter. And then when I draw this last shape, I draw it without the lone pairs. Same angles, same drawing. Can't change the angles. That's a bent shape for that end of the molecule. Just that end. Alright, so this is an uneven arrangement. Now, to know if you have something that's polar, you have to have 2 conditions, and an uneven arrangement of bonds is one of those 2 conditions. What's the other condition? It's the electronegativity difference that gives you what? Between 0.5 and 1.5, so you have to have polar bonds. You can calculate that. Calculate now whether this is a polar bond and whether this is a polar bond. Calculate whether these are polar bonds or not.